Now, there are lots of different ways that I could throw PVNert problems at you. You can solve for any of the terms in PVNert and rearrange, I suppose I should say, to get any of the terms in PVNert. And so long as I've given you enough information to either that you have the other three terms and are, or that you can find the other three terms, you will be able to get the last one. I've learned from long and difficult experience that I shouldn't give you problems like that dirigible problem on a test. Homework, it's fair game. Test, not so much. But these are the different ways you can rearrange. You know, P equals nRT over V, V equals nRT over P, N equals PV over RT, T equals PV over NR. You could also rearrange for R equals PV over NT. There's nothing wrong with that at all. I mean, how do you think they first calculated R? They took a gas about which they were very, very confident, and they measured the mass, they measured the pressure, the volume, the temperature, and they assumed it was an ideal gas. That is to say that it perfectly obeys the laws of kinetic molecular theory, and that works out just fine. But we, instead of spending a whole lot of time in these lectures on problems like that, we're going to go ahead and move on to molar mass, how you measure molar mass. That's actually surprisingly straightforward. All you have to do is go from PVNert to the dirt pile. Yes, I will be explaining that in about 5 seconds. Okay, so we start off with PVNert. PV equals nRT. Now, some of these things are not so easy to measure. In fact, pressure, volume, and temperature you can measure directly. Moles, not so much. So let's start with some things we can measure, and we'll play around with them a little bit and see how long it takes us to find something a little bit different. Let's say density. Okay? Density is equal to mass over volume. Okay, that's kind of useful-ish. Let's also take a look at molar mass. Molar mass is mass over moles. Okay. I'm going somewhere with this. All right, so let's go ahead and rearrange that one so that moles is equal to mass divided by molar mass. And then let's go ahead and rearrange density so that mass is equal to density times volume. Well, you just go ahead and plug that top equation into the lower equation, and you get moles is equal to density times volume divided by molar mass. Still doesn't seem like we're heading somewhere? Oh, we definitely are. Okay, let's go ahead and plug moles back in up in PVNert, and or dV over M in for moles. And that gives us PV equals dVRT over M. And, oh, look at that. The volume cancels out, leaving us with P equals dRT over M. The thing is, we can already measure pressure. We don't need to calculate pressure, so let's rearrange that just a little bit, and that gets us M equals dRT over P. That's what I call the dirt pile, just because I'm very bad at coming up with mnemonics. If you can come up with something better, I welcome it. I probably won't change anything because I'm stubborn, but hey, there you go. Molar mass is equal to density times the gas constant times temperature divided by pressure. Those are all nicely physical things you can measure. That's just mass over volume times R times temperature divided by pressure. And that is how they found molar mass very frequently back in the day. It's not perfect. It only works for those ideal gases, but dang if it isn't a really good start. It's actually measuring molar mass using stuff that you can, actually get a handle on physically. All you need is density, temperature, and pressure. That is pretty gosh darn awesome. So let's go ahead and do one really, really quick problem and see how that works. Okay, so let's roll through this really quick. We have a gas with a density of 3.2 grams per liter. But that's not enough. We also need to know the temperature and pressure. Well, it's 3.2 grams per liter at STP. STP is standard temperature and pressure, meaning 0 degrees Celsius and 1 atmosphere. Okay, so let's go ahead and plug this into the dirt pile. M equals dRT over P. Plug in the numbers. That gets us 3.2 grams per liter times 0.0208206 liter atmospheres per mole Kelvin times 273 Kelvin conversion divided by 1 atmosphere. Okay, and do the units work out? Yeah, liters cancel, atmospheres cancel, kelvins cancel, leaving us with grams per mole, which is exactly what we need. And once you plug those in, you get 71.7 grams per mole. Now, looking at the periodic table, you might be tempted to think that what we're looking at is gallium or germanium, and you would be wrong. Okay, those are not gases at STP. Okay? Those are a metal and a semi-metal. Okay? They're quite solid at room temperature, or at 0 degrees Celsius. Okay? They're frozen at freezing. So no, what we're looking at is actually chlorine. Yes, chlorine gas. And the reason we got an answer that was close but not right is because that's a density I found in 5 seconds of Googling. Obviously, it wasn't a very good density. But yeah, that's a dirt pile problem. You can do it in other directions, things like that. It lets you predict, for example, the density of gases at various temperatures and pressures. Interesting, useful. Breaks down, at cold temperatures and things like that because liquids. But it's neat that you can actually get molar mass out of simple physical values. But let's go ahead and move forward. And we're moving forward to real gases. Now, this whole time, we have been talking about ideal gases. An ideal gas is a gas that lives up to the expectations of kinetic molecular theory. Okay, that particles don't have volume, that they don't interact except when they collide, that those collisions are perfectly elastic, and so on. But there is almost no such thing as an ideal gas. Some elements, at least helium, when you cool it down and get it really, really cold, some things can act as ideal gases. They act really, really weird. But for the most part, gases are real gases. They don't live up to the expectations of kinetic molecular theory. In fact, they violate 2 of the laws. Specifically, that gas particles have no volume. Well, obviously, the particles of a gas do have volume. Okay? They're actual physical things. They're made of matter, and matter is anything that has mass and takes up space. So what you do to come up with a description of a real gas that takes into account the fact that the particles have volume is with the correction here on the right. Okay? Instead of V, you use V minus NB. N is the number of moles of the gas, and B is the amount of space taken up by the gas particles. Volume per mole taken up. Okay, so what you're doing is you are making making the space available for the gas to move through smaller by just removing the space that other particles are taking up. Okay? And that is a very straightforward correction. The next correction, not so much. It says that gas particles do interact. Okay? They feel attraction for one another. They feel repulsion for one another at very, very close proximity. It's a very complex and confusing sort of thing. But what we do is we apply another correction, which you can see is much more complicated. Instead of the regular pressure, we use pressure plus a correction taking into account the fact that when they get close to each other, their electron clouds repel. So that pressure is equal to the ideal pressure plus A n squared over V squared. A is the correction factor, N and V are the moles and the volume. Okay, so the greater the volume, the smaller that correction factor is going to be, just because the particles will be further apart from one another. And the greater the number of moles, the greater that repulsion is going to be, because there are going to be more particles to interact with one another. Okay. And that A is just something you have to measure by looking at the gas and comparing it to how it should behave as an ideal gas. You use these two things together, these two corrections, the one to pressure, the other to volume, and you come up with what's known as the van der Waals equation. That P V equals nRT has become P plus a correction factor times V minus that correction factor equals nRT. So it's very, very similar. Okay? It's pretty much the same equation. Now, I am not going to ask you to do math with the van der Waals equation. It's interesting. It's a surprisingly effective equation, and you can get a lot of learning out of it, but it's complicated math. The important thing is to remember that those are the two laws that real gases don't quite obey. The other thing you need to remember is when and why gases do behave ideally, or almost ideally. So the first condition of ideality is that gases don't have volume. And the way you approximate that, the way you approach that, the way you make a gas get as close to that as possible is by making sure that the volume of the individual gas particles is really, really, really ridiculously small compared to the total volume the gas is occupying. So that means you want your gas to be really low density. You want the gas particles to be incredibly far apart. Meaning that you want your pressure to be incredibly low. And that's when you have a low density gas, is when when the pressure is incredibly low. Okay, if there's just not much gas per unit volume, then the particles can't bang up against the walls with a whole lot of aggregate total force. So low pressure. Okay, low pressure tells you that you don't have many moles per unit volume. Okay, low pressure means low density. And for the other one, particles not interacting. Particles interact when they have time to interact. Okay. Again, going back to magnets, you have magnets on a tabletop. You slide one magnet toward the other slowly, then it won't actually get there. It'll sort of semi-bounce off. It'll get close and then curve away. But if you flick it really hard, it'll bank. It'll actually smack into the other one, and then they'll fly apart. Okay, so to limit the interaction of particles, you need to limit the time available for them to interact in. You want really high temperatures. Okay, so those are the two sets of conditions that real gases come close to being ideal. Okay, low pressure, high temperature. And neither of those should be too surprising, because a gas behaves ideally when it is as far as possible from being a solid or a liquid. That means high temperature. You heat things up, they boil, right? They become more and more gas. Okay. High pressure. You squeeze things together, they're getting closer and closer together, then that's when they become liquids and solids. Almost everything out there, you put enough pressure on it, it'll become a liquid or a solid. You heat it up enough, it'll become a gas. You cool it down enough, it'll become a liquid or a solid. There's really nothing out there that will violate those conditions. So, low pressure, high temperature. I'm repeating that because I really want you to remember it. All right. And now we are coming to the end of this particular lecture. It's been about 15 minutes, so I'm going to go ahead and call an audible on this one, and this one perhaps a few seconds early. And I will see you in Lecture 14.